Hello everyone. Now, here we are going to approach some types of problems that require modular multiplication. This one is sort of analogous to a problem we did before with addition, where we're given some sort of limited information and asked to find information about the remainder. So, let's look at it. The remainders when two natural numbers are divided by 12 are 5 and 9. Part A asks us to find their remainder when their product is divided by 12. And then part B asks us to find the remainder when the product is divided with 4. So let's establish the facts that we know. We have two natural numbers, which I'll call A and B. And I know, for instance, that one of them, when divided by 12, has a remainder of 5. So I'm going to say that A is congruent to 5 mod 12. Because that's exactly what that means. If you have a remainder of 5 when divided by 12, then that value is congruent to 5 mod 12. The other has a remainder of 9 when divided by 12, so I'm going to say that B is congruent to 9 mod 12. So those are the facts that we know. And wants us to find, part A at least, wants us to find the product when divided by 12, the product of A and B. So that means we would multiply them together. So A times B. Well, according to the previous theorem we have established, that product is going to stay the same even if we multiply to 5 and the 9. So let's do exactly that. 5 times 9. And that would become, well, 5 times 9 is 45. And when divided with 12, 45 has a remainder of 9. So that's congruent to 9 mod 12. Now, let's continue even further. Well, I mean, that's basically part A. Pretty light work, right? Part B, like we saw last time, is going to be a little bit more work. But let's see what we can do. So, we don't know anything about mod 4 right now, so let's start with the information that we're given. If I know that A is congruent to 5 mod 12, then what I can establish is that A minus 5 is equal to 12 times K. It's a multiple of 12. The difference is a multiple of 12. And if I add 5 to both sides, I get A is equal to 12K plus 5. Again, like we did in that addition version, we're setting it up to be analogous to the division algorithm. And the other piece of information that I know is that B is congruent to 9 mod 12, so their difference is a multiple of 12. So B minus 9 is congruent to 12 times J. And adding 9 on both sides, we have that B is equivalent to 12J plus 9. where j is an integer, and so is k. Alright, well, how can we get this into some sort of form where we can predict what it would be equivalent to mod 4? Well, what we want to show is that both of these equations can be written in such a way that we can demonstrate that the difference would be a multiple of 4 times an integer. So again, a little bit of trickiness is required. I'm going to write that a is equal to 12k. Now 12 is a multiple of 4, which is good. That's good to work with. But 5 isn't. So I want to rewrite 5 in such a way that it is a multiple of 4 in a way. Not 5 itself, but something I can work with. Like, for example, 5 is 4 plus 1. And that way, I can factor out a GCF of those two terms. The GCF would be 4. So factoring out, or think of it as reverse distribution, this becomes 4 times, well, 4 times 3 is 12, so I'd have to write 3k here. And 4 times 1 is 4, so I have to put a plus 1 here. That way, when I multiply it back in, if I had to, I would get the same 12k plus 4. But I also have this plus 1 on the end. Now, I can subtract 1 on both sides to demonstrate that the difference between a and 1 is equal to 4 times 3k plus 1. And what this establishes, well, 3k plus 1 has to be an integer, because 3 times k is an integer, and plus 1 would be another integer. And if the difference between a and 1 is a multiple of 4, then this establishes the fact that a is congruent to 1 mod 4. So that's pretty interesting. Now, what can we do? What can we do? What can we do? This is still part B, but I'm trying to separate my work for A and the work over here. So what can we do with the next part? Again, looking for multiples of 12, I'm going to rewrite, not multiples of 12, multiples of 4. I'm going to rewrite 9 as 4 plus 5. And in a similar manner, factor out a 4. We have 4 times j plus 1. Not 4 times j, 3 times j. 3 times j. Because 4 times 3 gives us the 12. So 3j plus 1 times 4 plus our 5. And again, subtracting by 5 on both sides. This will establish the fact that the difference between b and 5 is a multiple of 4. Because it's 4 times some integer, that integer being 3j plus 1. And again, it doesn't matter what 3j plus 1 even is. All that matters is that it is an integer, and an integer multiplied by 4 means that that must be a multiple of 4. And since the difference of b and 5 is a multiple of 4, we have established that b is congruent to 5 mod 4. So now we can take the two pieces of information we have and put them together. Namely that a is congruent to 1 mod 4. B is congruent to 5 mod 4. So to answer part B, find the remainder when their product is divided by 4. Well, let's find the product. So we have A times B, which is congruent to 1 times 5, which is congruent to just 5, which is congruent to 1 mod 4. So the product AB is congruent to 1 mod 4. So, given very little information, we can find some very interesting properties of remainders when divided by certain numbers.